Are people going to wander in, but in the interest of finishing in the hour and giving you time, I suggest we start, all right? We're fortunate to have Professor Yong Chen, of our own School of Marine and Atmospheric Sciences. His research is in quantitative fishery ecology, population dynamics, and fishery stock assessment and management. I won't read all the details, but he's quite accomplished. I've loved the 350 peer-reviewed. That's very, very accomplished. And today we're going to learn using computers to manage the fisheries.
Yeah,
thank you so much.
Yeah, thank you for the intro, and thank you for the invitation, to give a talk. And so I'm relatively new to this university. I moved here actually 2021 together with some of my students, and I used to work at the University of Maine for more than I would say more than 20 years. So I just a very brief intro of my lab. I do have a big lab. I have about 25 people in my lab now, covering. This is a 5 research topic that we covered in my lab. One is the first one is the fish stock assessment. Basically, when we talk about stock assessment, we talk about how you could design a monitoring program to collect the data, and then you develop models and identify stats approach to feed the model to the data, and then you estimate how fish population changed over time and over space, and then you provide this information to management agencies to develop catch advice. That's a stock assessment, and then we also work on climate change and fisheries ecology, how that may affect ecosystem dynamics. And my lab also run a historical Hudson River biological monitoring program, which is actually why I came here, because this is a data that collected by utility companies over time. I think since 1974, it was donated to the Stony Brook universities. So you see tons of data, and we have about 50 million samples. Actually, we ran a bigger warehouse in Port Jefferson Station, and all those samples. So that's a really valuable resources that we just started to get into it, and a lot of opportunities and for collaborations, and because such a big data set, a long time series, and also all the environmental data also collected together with the fish samples. So that's just want to make sure that if you are interested for collaborations, that definitely there will be a huge database that we can work together. And then also engaged in management and policy development. I'm sitting on a lot of NOAA's committees, and basically look at how can make a science, how can make a decision and management regulations based on solid science. And also my lab runs an international collaboration program, trying to promote sustainable fisheries, more kind of focus on the science-based. So working with a lot of different countries, and those are programs mostly funded by foundations. So those are some of the members of my lab.
You had an REU student this lab, right? Yeah, am I remembering that right?
No.
No. Okay.
Yeah. So the when we talk about anything, we always start with what would be the objective. So I think for me, marine resources management objective, there are 3 objectives here. One is you want to maintain resource productivity, right? And you want to make sure you don't deplete your population, and you want to make sure that the productivity is going to sustain for a long time, right? And then at the same time, you also don't want to just you want to take an opportunity to utilize these resources. So those would be how can efficient use of resources and to serve a human and to serve a society. And then again, we all have a different views on a lot of things, and I think management should try to resolve conflicts among stakeholders. So those are 3 major objectives, but they are based on, I think, the first one, you have to maintain resource productivity. So how can we do that? That deal with management. Now, fisheries management, I think that very different from a lot of other things. You have to consider human behavior. So usually in a system, we have 2 kind of things that we have to consider. One is a resource state, and the other one would be a human component. And you can see that this diagram. I think I really like this diagram. It really tell you, all the key components that are included in the fisheries management. And thing here is that we have 3 basically three central part here. You have a fish operation, and you have assessment system, and you have decision-making system. And for that, each one of them, you have reporting, and monitoring and assessment. And then for decision-making part, you have an implementation and how you're going to make a decision. And operation part, you look at into this all the background information, background dynamics and ecosystem dynamics, and then look at the fishery operations and so on. So the key here is that because this is a big, a very complex system, and you would not be able to collect all the information that you want, and that created a lot of uncertainties. I mean, you look at all the uncertainties, right? And so the key in fishery management is that you have to make a decision. You like it or not, whether you have data or not. Every year you have to make a decision for management, and based on limited information. That is, you have to make a decision under big uncertainty. Now, all the research we try to do is to try to reduce those uncertainties. I mean, if you are sure about a stock status, and of course you can manage a better way. You can try you will minimize the likelihood of overfishing the population. Yet, if you made a big mistake in your assessment, likely you're going to make a wrong decision. You either overuse or underuse the resources. Right. So all the research that we'll be doing here is to try to reduce those uncertainties from different sources. That's the key. So with that, and in fish management, we also have to consider what kind of tool we're going to use, and the tool we include monitoring, assessment, and then MSC is a management strategy evaluation. It basically is a very complex computer simulations, try to mimic what happened in fisheries, both on the resource part and the human part. So that's a management strategy evaluation. That's a tool that we often use. And then in terms of method, we can have expert input, empirical observations, and then you also can have a very, very complex model. And in terms of scope, that things we have considered, simple one would be just the fish population, but we know that they're not living in the ocean by themselves, and we have to consider the ecosystem, and because of human involvement, and you also have to consider socioeconomic. So that kind of a scope, the complexity of the scope increase exponentially when you consider all those key players in the fisheries. And but this talk, I want to focus on more on the fishery part, on the resource part. How we can reduce uncertainty with the help of computer simulations, right? And so that we started with the model. This is the type of model we often used in fisheries, but I think in general in ecology, and it would be both a statistical model and compartment model or process-based model, right? And empirical model, statistical model, we know that you have a data and you try to use a statistical approach and try to find a relation. And for the process-based model, you have to, based on your understanding of the high population change, ecosystem change, and then you build up the model. So it's a process-based model. And both of them have a pros and cons, and both of them can serve a different purpose in fisheries management. And then you see that the model getting really complicated. Before with I remember when I was a graduate student in 1990s, we still use like a 385, 386, 385. It's very slow, like simulation take like a week basically, and now probably take a second. But that really the complexity of the model really changed, and now go all the way to what we call an end-to-end model. That is, you basically incorporate all the elements in the ecosystem, all the way from nutrients to the fisheries management. What is called end-to-end model? That very, very oceanographic, processes and also decision-making processes, and all incorporated into one model. And so that really complicated. But again, the complexity increase over time. This is a year, and also computation needs also increase exponentially with the increased complexity of the models. But step back a little bit, we do have a lot of choices on those models, but the goal for our research is to figure out how fish biomass changes over time and over space, right? And you have to think about it. it's a very complicated process, but you have to isolate all those processes. But look at that biomass, it will be affected by two mortality. One is called a natural mortality, it because of a predation, disease, whatever, cause the death. That would be the natural course. That would be the natural mortality. And then you have a fish mortality. So you have recreational fisheries and the commercial fisheries. And so that would be mortality. Those are reduced biomass. And then you have a recruitment come from, from the sponge stock biomass that increase the biomass. And then you have a growth that would be the increase of fish size over their ages. So those are kind of a positive impact on the biomass, and then the two mortality will be negative, have a negative impact on the population biomass. So yeah, it's a complicated, but it's also simple. But if you can figure out all the natural mortalities, or how recruitment getting to the population, and how the growth fish grow over time, and then you should be able to figure out the biomass. But of course, that's simple. But we need a data to do that, right? And also those are processes not isolated. That's a problem, because if they're isolated, that's straightforward. But they're not isolated. They are affected by a lot of oceanographic processes, and they are probably density dependent. Density dependent factors may regulate that process, and also they probably change because of that. They change it over time and over space, and so that makes things really complicated. So the assessment, the future stock assessment process, usually include the three parts. You have all the data, we call it input data, and you have a model. You feed the model to the data. And once you have a model fitted, and you're going to decide, your stock status, and then with that you're going to make a forecast. Now, forecast will give you what we call OFL. There's an overfishing limit in the U.S. That's by law. You have to set up OFL. That is the highest ever you can fish mortality you can have. If it's higher than that, your fishery will declare to be an overfishing occurred. So that's a OFL. That's basically, it's a limit that you can have. And then we have an allowable biological catch or annual catch limit. That is supposed to be your catch target, so total allowable catch for a given year. And we have to set up for all federal managed fisheries. We have to set up those limits. And the goal is that we try to answer those 4 questions. All the complexity, all the hard work, we try to answer these 4 questions. One is what harvest policy is sustainable and provide a balance between preventing overfishing and attaining maximum fishing opportunities. So that, remember the 2 objectives, those are 2, right? Try to balance there. For that, you have to figure out what would be the reference point. What would the highest fishing mortality or optimum fishing mortality, and what would be the optimum biomass, right? You have to maintain for the population. So that's 2 things you have to figure out based on all the modeling work. And then the second one would be, based on that, you're going to figure out when you're going to define overfishing occurred. When you think that fishing mortality is too high to declare overfishing occurred. And then you have a biomass problem. You're going to figure out when you're going to decide, when you think that a biomass is too low and to sustain the population, right? If it's too low, then we declare the population is overfished. That means it's too low, right? So those 2 things are really important in the federal managed fisheries. And then, of course, managers for future, right? And we want to make sure that we understand it. And we have to make a forecast. So say, hey, what a level of fishing mortality that you can have, or total removal you can have for next few years without hurting the population. And at the same time, you don't waste the fishing opportunities, right? So that's 4 questions that we try to answer in stock assessment. And this is a science manager framework that we use, what we call in the US called council process. And council, we have a national stand for fisheries management. National stand number 2 is use the best scientific information available to inform fisheries management. Those are measures that we have to follow them. Now, in order to do that, and we have a console process, we start from data collection and run assessment, and then we have extensive peer review processes. And depending on regions, we have 8 consoles in the country, and in the east coast, we have a New England Fishermen Council, and then we have Mid-Atlantic Council and South Atlantic Council. So here, New York, I think, is part of the Mid-Atlantic Council. And so we have, those are process review, and then we have, once a review, once the assessment is accepted, and then it will be utilized for decision making and management. So that's a council process. So this is a typical assessment framework, a model, and you can see the database, and you can see a whole bunch of models, right? Model and submodels that describe all the refugee processes and how population, the process that affect the population dynamics. And then you have a decision making, like all information that provide a decision making process. So that's the 3 big components in any assessment. So yeah, so those are kind of just give you a quick background intro about fisheries management. And you know that, hey, data are really important, right? We need the data to figure out what is the stat of fisheries. And then you know that you need a model, right? You need to do stats and to figure out, to feed your model to the data. And then you need to figure out, the stat of fisheries, and then you need to figure out how you can make projections on the different regulations, right? Because every year we only have one chance for management. You cannot like agriculture, you can, within the room, you can have a different treatment, you have different tanks, you have a lot of opportunity to replicate it, but in actual fishery management, you only have one chance per year, right? You have to figure out before actually that year started, you have to figure out what would be the total allowable catch for this year that can balance the, protection of resource, conservation of resources, and human utilization, right? So that's in order to do that, I think the very, very important part is that we need to reduce uncertainty. We want to know how exactly population dynamic change, how ecosystem may change it. So those are uncertainties actually, result from those are, I listed a few uncertainty sources, and you can see that, uncertainty probably from that spatial temporal variability, that it always a change from year to year. And also, oceans are huge, and we have so many fishing ports too. When we have so many fishing vessels, think about all the complexities when you try to collect the data, right? The different fishing gears, different fishing vessels, and different targeted species. And so that comes with the sampling variability, measurement errors, and how you can collect the data that best represent all those the differences, right, in fisheries. And then we have a uncertainty population model. We all know that model is the hypothesis that you have about how population changes, and we don't know the true answer. So that's another uncertainty that we don't know whether the model that we use actually truly represent how population may change it. And then we have even if you did everything wonderfully and you have make a recommendation for management, and you probably have also uncertainty management control there, because the enforcement, you will not be able to keep tracking everybody's what they are doing. And so there are a lot of uncertainty associated with that. And then that relate to the fishermen's behavior and the fleet dynamics. People change their strategies, and sometimes you change the regulations, they change the strategies, and probably compromise the effectiveness of your management strategies. And so that's a very interesting interactions, between the management agencies and industry, and that pose a big uncertainty in fisheries management. And then you listen about dynamics of fishery market, because you catch fish, you try to make a money, right? And there's a market actually will, a lot of time, will dominate how fishermen make a decision. And so sometimes even you have a very high quota, you have a high total allowable catch set for a fishery, and the fishermen probably won't catch it because they just think that they're not going to make a money out of this. So that's market is another very key factors.
That's a good question.
Yes, yeah.
Because it relates to, I think, computation Are these decisions that are being made during the season that where it's really urgent that you get the model estimates because you're gonna turn around and tomorrow they might change the policy? Or is this sort of between seasons setting the policy for the next fishing season?
Yeah, so most of the time, it's before season, not in season. Because in season, you have to keep checking, right? And we do have an in-season monitoring program, but it's more like a make sure that this year, your total catch will not be higher than the target, right? But that's the only thing that we do. But in-season management, that's very costly.
Yeah.
Some fisheries, yes, you do have that. If you see that very valuable fishery like some snow crab fisheries in Alaska, they do have in-season management regulations. You can stop when they stop, they can change the strategy. Yeah, during the season, but that's very costly. Yeah, most fisheries, we don't have a in-season management strategy. So that means that we need research, right? All those uncertainties, we want to have a better understanding of those systems, and we want to reduce the level of uncertainty. And so, a lot of research that in fisheries that they probably have a different topics, but a lot of time the research will develop, try to optimize the monitoring program, and try to develop better model estimation methods, and try to better quantify population dynamics, and also try to develop more kind of alternative management strategies that are less sensitive to uncertainty. And also, we want to develop a framework to incorporate uncertainty decision-making process, and again, try to study to understand the fleet dynamics and the impact of socioeconomic factors. So those are kind of in general that research that we needed. And so given that, and you think about it, what computer simulations can play, the role of computer simulation can play in that process. So there are a lot of different ways using computer simulations, sometimes larger scale computer simulations to help reduce uncertainty, to conduct the research in fisheries. So we have, one is you can evaluate and optimize sampling designs, and you can evaluate and compare performance of different models. And you also can look at, identify roles of various factors, how they may affect the stock assessment and management. And then you can evaluate the performance of a different harvest strategy, or harvest control rules that we call it, used in fisheries. And you can also evaluate alternative management strategies, because you're going to, every year you're going to evaluate a suite of strategies, and then you try to pick up a good one, or optimum one, and that's when you use a larger scale computer simulation. And then of course you can identify risk associated with certain type of strategies. And so that's you can have a long list of, I just listed some of that. So in this talk, I only have that amount of time, so I just want to cover that 4 case studies quickly. One is evaluate the performance of sampling design, and the other one is the next one is evaluate the consequence of violating assumption in assessment, and then evaluate the impact of conservation measures, and then the last one is to test the performance of the stock system. So those are the 4 that we have done in the past. I don't know how many years, but done in my lab. And so the first case study and is about how we can evaluate the performance of the sampling design. And so the simulation start from you have actual survey data. People usually run a survey extensively for a few years, and then you collect the data. For this one, and with this data we can calculate the habitat modeling, and then with habitat modeling we can simulate fish population distributions, and then with that distributions, and we can test a suite of proposed sampling strategies, and then do the comparisons, and then eventually identify optimum one that we'll call a cost-effective sampling strategies. So that's kind of the diagram that we often use when we try to evaluate a survey program or a sampling program. So this is this case study focused on a tall survey that conducted by Maine Department of Marine Resources along the coast of Maine and New Hampshire. It's a coastal surveys, and it's a biennial survey. You have a spring and fall survey, and you got to It's about a little bit more than 100 stations along the coast. And so what we do here is that for the model, we use the data, right? And we create habitat models and then identify habitat models, and then we validate them. So we set aside data for model building, and then set aside some of the data for model training and for model validation. And then once the models are validated, and then we use the model for prediction. And the prediction, then we map up the fish distributions along the coast. And then we apply the different sampling strategy or survey strategy to the simulated populations, and then we do the comparisons. Because when you simulate the population, we know the answer, right? So that's the beauty of the simulation. So that one, and also we have to consider the biological factor, because this one actually focuses on American lobster, which is the most valuable fishery in the US, 10% of the total fishes output. And American lobster, there are different life stages, they have different preferred habitat. So we have to actually separate them, juvenile and adults. And the different seasons, they also have a different preference, and the different sexes, female and male, they also have a different. So we have to separate them and consider all those factors when we try to model their habitat. And so that's what we do. And we, listed all the data we have, and we, identify some key environmental variables on the spatial variable that may influence their distributions, and including into the model, right? In the model, and then we tried different models. And so this is the model that we use. We call it two-stage general additive model. So we have stage one is basically look at presence absence. And then stage two, we when they present present, and we're going to look at their density. So that's a two-stage, and then you put it together, and then you look at it, because we have this, we have those things that we have to consider, and that resulted in a total of 16 models that we need to construct. And then we have the models, and then you look at the performance of the models, right? Remember, we set aside a part of the data for validations, right? So that's a validation that we have, and we find actually the model performed really well, and so that means that we will be able to use this model for projection, right?
That's just because, so the model was assessed on the basis of withheld data, like its ability to predict data that was not
included.
Not included. Okay.
Yeah. So that's a kind of fair, instead of look at the R square, that,
Right.
of course you're already building into the model.
Yeah.
So that's the model outside. Yeah. So this one is that is what we use for projections, and we predict it, and then you can look at it, the lobster density distributions over time, and you see different areas, and that those are the color, of course, represent different densities. The red one means that I think it's this is a 100 square meter or something like that. The unit is about if it's red, then over 20 lobsters. So that's a pretty dense. And but that once we have that, we can apply different strategies, different sampling survey strategies. And then we can calculate sample mean, and then do the comparisons with the true value building values, and to compare the performance of a different design of the surveys, right? And so this is so we actually talk to main Department of Resources to ask them, say, hey, now you have this is what they have right now, design 5, the one that they use, and we want to ask them, hey, what kind of strategy you want us to test, and what you think is feasible. I mean, when you design a survey, you have to think about it, whether you can afford it, because it's costly is always a problem, and also logistic too. Right? If you have too many, of course you get a really nice data, but you cannot afford it. And at the same time, also the logistically, you probably would not be able to implement it. It's too complicated. So we identify together. We identify 5. This is a what it actually conducted, and then we have a stratified design with a 4 depth strata. Now this one has like a 4 depth strata and 5 regions. This is the forget about region, and we just only have a 4 depth strata. And then this is only stratified by 5 regions, and then we have a systematic design, and then we have just a simple random design. So those are 5 designs that we used in the surveys and the testing survey, and then we can find that this is a kind of a measurement of errors, and of course the lower the better, right? And this is with a different sampling intensity. So we have 87 stations, 115 stations, 144 stations. I think this is what we have right now, 115 stations. So instead of 5 designs, this is what they have. And if you look at this one, you will see, wow, this is the systematic design, right? It's the second one. It has the lowest, but systematic design has some issues because you look at this one, lower 87 stations, it's a pretty high, but you have a 115 stations, it's very low, and then you increase the station, actually the error become increased. So that's not it's a lack of consistency here. When you increase the sample size, you're supposed to reduce the error, right? So this one is a kind of weird performance, and but you look at the others, and this one actually probably relatively, look at it, compare this one with this one, this one with this one, this one with this one, and this has the lowest error term here.
That's my question as to whether like travel time between stations was included in, like, do you have to pay to travel between locations, or do you just assume that all 115 locations are equally easy to get to, no matter where they're placed?
Yeah, so I think no matter whether you have a design and the order of surveys in terms of how the station is covered, it's always the same, so that making them comparable.
Okay.
Yeah, so yeah, but that's a really good. That's a really important consideration actually, because we're thinking about cost here and the time. You have to finish everything within a time limit, right?
Right.
You cannot, you cannot.
And that's where like a clustered sampling design might minimize travel time between stations. You know what I mean?
So we the one here we didn't consider cluster design here, and this is all more like stratified random survey. Yeah, but I think that's something that will not be used in fisheries. So this one is this is if you look at we look at this systematic survey, and we think systematic survey I think it would be easier a lot of time because it just random pick up one photo but that performance is kind of weird, and then we look into that instead of like a 3-level sampling intensity, and we actually look at it all one we just plot that and with a different level. Different level of a different number of sampling stations, and you can see that actually they are fluctuating. So that means that the inconsistency in systematic design, and so we kind of worried that yes, we have the data used right now and give us this really nice results, but what happened if that distribution changes and the error might increase? So even though in this one, systematic design probably perform best, but we have a concern of the consistency. So eventual recommendation is that we stay what we are, and I think Maine Department of Marine Resources are happy with that, and they still continue using the work that we've done here and continue have around 100 stations and the same design over time. So that one is a really kind of a study is really nice, assure that their design is good and produce reasonable results. So my second case study is looking into the how the performance, how that the performance of the model can be compromised by violation of some assumptions. So again, this how there's a kind of flow chart of the study. We start from input data, and then we develop what we call a fishery simulator, and then use a simulator to simulate fisheries, and then you have output from that simulated fisheries, and then we use that as input information, and we actually run a stock assessment, and with the stock assessment, and then we have different perceived assumptions in those models, and then we say, look, hey, what if you violate those assumptions, and how that may affect the results. So then you compare that with the true answers, and do the comparisons, and then you figure out, that would be the impact, and you make sure that you consider that impact in your decision-making process. Oops, I'm way ahead of myself. Almost pretty fast. Yeah. So this is the feature that we actually try to use here. This is what if we ignore mixing our fish among the Gulf of Maine, Georges Bank, and the 4X is a Canadian cod fishery. This is Atlantic cod fisheries. So the 4 stocks here, and there's exchanges of fish move around. But any stock assessment will do. A lot of time we assume that there's no movement. This is a closed system, right? So apparently there are movements of fish between different stock areas that violate assumptions. So what we do here is that we build up models and incorporate that movement among different stock areas, and then we do the assessment, and then we look at what happened to the results. And so this is a measure that we use to measure the errors. And so I'm very complicated. This I just want to point out, this the top one here is that you see the true non-mixing and assumed non-mixing. So that's a consistency, right? They're saying, and you make a right assumption. So then you look at that. This one is really nice. This is an SSP, sponge stock biomass estimate, and this is a SSP status. So they're really nice, unbiased, very nice. And then this one is choose is a mixing. There's a mixing, but you're not considering the assessment. And you see the bias here. This is underestimated status, and this is overestimated stock biomass. And so you see the impact. And the same for other measures. So that one is the sponge stock biomass. This is the recruitment, and you also see non-mixing. And then there are some little bit of bias here, but for this one. Violated, and then there are mixing, there are errors too. So look at this one; they're not very similar, right? Most of them have issues and have errors. So for recruitment, and even though you violated assumptions, and they're very similar, performance-wise. And then you have a fish mortality estimate, and again, they're very similar. This part is there's no violation of assumption, and this one is a violation of assumption. And you see that performance is still very comparable, at least. And they're not exact same, but they're compatible in terms of error term. And so the conclusion here is that yes, if you don't consider stock mixing when it exists, and may result in extra errors for sponge stock biomass, and but assessment model tends to be rather robust to that specification. There are errors, but the errors are not that huge. And actually, we found that the quality of the data actually more important than the violation of the assumptions. And so that is the conclusion that we have. Actually, that conclusion was utilized by North Fisheries stock assessment for Atlantic cod back quite a few years ago. So the third case study I want to highlight here is that how we can use a computer simulation to evaluate the impact of conservation measures. My apology for the how busy it is, but in American lobster fisheries, there's a conservation measure called V notch. That is, you look at the one here. This is a V knot. Is a sign of a V here, right? And so when fishermen caught a egg-bearing lobster, there's a lot of eggs here, and you cannot land them, and you have to let them go. But before you let them go, you have to have a V notch, right? And that V notch actually can survive in 2 molts. So the bigger one probably they don't molt every year. They probably molt every few years, but they can survive 2 molts. So the molt ones, you still see this sign here, molt 2, you probably still see that. But after the 2 molts, they probably disappear. Whenever fishermen catch a V-notch animal, and they will not be able to keep them, they have to let them go, even though they don't have eggs. So that V-notching program actually can protect the egg-bearing lobster for, not egg-bearing, the mature lobster for quite a long time, quite a few years. And you look at this, how the timelines and how lobster regulation changed, and you're going to see that in even 1889, it was illegal to catch a burial female, and that program actually started. I think it's 1948, and so that's industry started program. It's not even government started program, and I think we believe that this program actually contributed to a dramatic increase. And one of the important factors that actually contributed to that dramatic increase in lobster landings here. So this is a kind of paper that we published a couple of years ago. And so their simulation work starting from the building an individual-based lobster fishery simulator. And so you look at this one, this started from this is a fishery, basically the kind of algorithm that try to mimic how fishermen make a decision whether a lobster will be landed or discarded, right? And because of the protection measures, that lobster has a legal size. Actually, they have a maximum legal size, and also has that V-notch improvement. And so that when they have a V-notch lobster, and you cannot land them, right? If it's not V-notched, and then if it needs V-notched, and it will be V-notched. And then this is a fishery part, and explicitly building to that protection conservation measures. And the other part is a growth, life history, and how lobster grow. So unlike a fin fish, lobster don't grow all the time. They grow like stepwise. They don't molt. When they don't molt, their size will not change, right? So after a certain time they molt it, and then when they molt, the size increase by a pretty big number, right? So that's how we'll call it stepwise growth. And so this is to describe how the lobster change their size. And then we use that individual-based simulator. We simulated billions of lobster, and that cost a lot of time, computation time, of course. And we are, always changing the algorithm, make sure that running very efficiently. We have to trace all individual lobster under their all the status, whether they're buried, whether they're mature, whether they're V-notched, and if it's V-notched, how many years they're going to be protected, and so on. So we're going to treat, we basically, each lobster is going to have a vector of their, either life history status or their protection status, and keep tracking until they either landed or died because of natural mortality. And this is we look at it simulated, and of course we compare the simulated lobster, simulated fishery with the actual fishery, and you see that very close. And then we test the different conservation measures. One is just want to highlight. This is 100% strict. That means there's no wiggling room. If it's V-notched and if the V sign, you have to protect them. There's no wiggling room. The other one is a little bit of wiggling room. It's not like 100% enforced. So if you look at this one, apologize for a very busy slide here, but if you just look at the 100, this is always the highest. This is the landing. So landing, if you look at the 100%, there's always it's a cumulative landing over 20 years. And you see that, even though, those are probably catch more, but over that evaluation period, and you V-notch the lobster, 100%, with 100%, the definition, it always has the highest landings. So that conservation measure really important. And not just the landings, but also when you talk about biomass, they're also highest too. So if you're like 100%, and that's a much higher than the rest, and this one is the highest, and this one is also highest. So whatever scenario consider, if you strictly enforce the V-notching program, and you're gonna get high landings, and your population level will be high. So all good for that. So you see that impact, right? So the conclusion is that without high V-notching compliance rate, and lobster stock probably would not have experienced such a large positive increase over time in both landings and in both biomass, right? So that really important. That is a conservation measure, actually protect the sponge stock biomass and also benefit lobster industry. So this is a last case study that I had, And, that's related to how we develop models. Because any models that you developed, and you have to demonstrate that your model can perform well, can capture whatever dynamics that might occur in your population, right? So what we do, we developed a lens-based, this one already used before, but this model is a lens-based model. And for this, again, for American lobster, this model, the reason that we use a lens-based is because it's very hard to age lobster, because they don't have hard tissue, right? Unlike a fish, you have otoliths, ear bone or scale or whatever, but lobster, they mold. So it's very hard to age them. And so that's why we developed this lens-based model. When you have a lens-based model, it's very complicated. And so this is a very, very complicated model. And again, 3 parts, we talked about that before. And again, this is a design of the simulation program. And so you have input data, and again, use individual-based. This is an individual-based lobster simulator. And then you simulate the lobster fisheries and output, and output you use as input information. Then you run this lens-based models, and then you output, and you compare with the data that built in, the dynamic that built in to figure out the performance of the model. And you can see that, we work with American Lobster actually is assessed and managed by an agency called Atlantic State Marine Fisheries Commission. So based in Virginia, actually, North Virginia. So we work with a working group, and we develop 10 scenarios to look at, how this model perform. And you see that, all involved names, and you see that, what happened if we introduce a bias in molding increment, and what happened if we introduce errors in the survey data, and what happened if we introduce in the fishery data, and what happened if we have a process errors, like the natural mortality, for example, and also this one we look at different patterns. So what happened if a lobster population have a 4-time increase within 11 years, and then within 5 years it's a decrease. So huge change within a very relatively short period of time, and whether your model can capture that, and or you have a flat and then 4 times the decrease, or you have a flat for 11 years and 4 times down. So that's all this different scenarios and different dynamics, and we want to see whether this model can capture those dynamics under all those error terms here. Remember all those error terms that we introduce it and do the comparisons. And so this actually, the program actually was run by Atlantic State Marine Fisheries Commission. And then you look at this one, I think so you have a true one, and you have a estimated one. Most time you can capture well, even though you have sudden decrease, the model can capture pretty well here. And even though you have increase and decrease, the model still can capture that. So that's really good. But at the same time, sometimes the model fail too. So when you have extra errors here, and you see that this true value actually true population actually decrease, and your model think that they're pretty good. So that's because of this is a scenario number 10, number 8, I believe. So that's when you have extra errors in natural mortality, and you see that departure. So that's something that we know that, hey, this model probably, when natural mortality is not right, you probably have some issues here. And this one's too. So you tend to overestimate it. And but through that exercise, we'll understand that when model may fail, when model may produce extra errors, and then we will consider that uncertainty in our decision-making process when we use the results, right? And so that's really good. And the same thing for other. This is more like a females legal biomass, right? And so this is my basically last slide. And this is I don't have time to talk about it. What we call the management strategy evaluation, and those are relatively new stuff. And I think, but expanded very quickly. This is basically like a computer game. You design a computer game. You use all the fishery data, you simulate fisheries, and then you try to manage that similar fisheries and look at the outcomes, and then do the comparisons of the different management strategies, and then identify optimum one, right? So this is like, you have operating models, and you feed the operating model with historical data, and then, historical data, and then you apply that into the stock assessment models, and then, do all the things like we have done for practical fisheries, and then try to manage that. And eventually we can see, hey, this strategy probably performed best. So this is the management strategies have been increasingly used in fisheries, but again, very complicated. And this is not even considered the socioeconomic factors here yet, but it's a very, very complicated process. And there's a lot of stakeholder engagement process there, because the people have a different, when you do the comparisons, you can have a different measures. Some people want to say, hey, I want a more catch. Some people say, hey, I want a more fish in the population. And some people probably say, hey, I want more money to produce from that fisheries. So there you have a different metrics that actually measure the performance of the model comparisons. So that's a really, really complicated process. But it's ongoing. That's why there are so many computer science students actually working in fisheries, because all of the modeling and exercise here. And so in summary, I think the computer simulation can help us improve understanding population ecosystem dynamics and identify limitation and errors we may face in fisheries management, and then provide guidance to improve fisheries. So again, fisheries, you think about it, it's very complicated. We try to find a way and to figure out where we go, and but it's good that we have those computer simulation tool that can help us. So those are I thank all of my students and also the funding agencies that receive to support all the work that we do. And finally, questions. Thank you.
About the psychology of management is whether you find these forward simulation models more tractable for non-experts than some sort of likelihood thing. You know what I mean? I just, because it feels like that is sort of like playing a game that they kind of imagine that you're forward simulating scenarios. I don't know how they receive that.
Yeah, so I think it's a really important question actually. So how you design the scenarios you want to include it, that's really important, because different stakeholders, they have a different interest, and they want to make sure that your model actually consider those are their interests. And so what we usually do here is that we have like workshops. The fisheries are very common, and you have stakeholders from industry, from academia, and then you can from government agencies, from state and federal agencies, and they come together. They put together test scenarios they want to include it. Yeah, that 10 scenarios actually take a couple of years to develop. And that actually lead eventually the adoption of the model that developed in my lab. So that the American lobster assessment actually in the US actually is done by the model developed in my lab. And I gave them the university name American lobster assessment model, but that's actually developed by my lab. And that simulation work played a huge role for federal agencies to adopt that model. Because we do have competing models, and we have like 2 rounds of peer reviews. It takes like 7 years to change the models, and so that's a very long process. Yeah. So that's I think how you include it or develop scenarios, that is really important, and it's not a trivial thing. Issues. Yes.
Hi, great talk. Can you talk about how expensive those simulations are? Computationally expensive.
Yeah, so for a lobster one, we actually have done quite a, we do a lot of simulations, and we have a project just finished actually using individual-based model. You have to simulate billions of lobsters. Just think about how many years, how the population there. And then we usually use our desktop. I have a really clear desktop computer, but it's really take forever, like a month basically. So we thank this institution, we actually have access to a supercomputer, and then you can do that in a day, for a scenario. And we just finished that actually, and we finished that project funded by fisheries, and look at the climate change actually, how climate change affect the lobster life histories parameters, like how they change their growth, and then how that growth changes the growth and maturation affect the population dynamics, and then affect the fisheries. So those are like we have to test like 100 scenarios because the different stakeholders give us say you have to do this, you have to do this, and we compile the big tables. I have a postdoc actually. He did all the simulation runs, but he finished work here. Now he's a no efficient scientist now working in Woods Hole. But it's a lot of computation time, and I think a lot of demand for programming skills, and also I think the understanding of the biology, ecology, that's really important. So I think in the US actually we don't have a lot of people actually study stock assessment because of its complexity. So you have to know the biology, you have to know the computer science, you have to know stats, you have to know all policy, and it's very hard to find a student who are interested in everything. Most of the students are actually interested in fieldwork and the biology part, but ask them to make a program. I have a player here, he's my PhD student, and ask them to do the modeling, and then have to communicate the result to the stakeholders. It's not easy, right? Money-wise, yes, it's a very hard to hire very high scale postdoc. I don't know Heather, you have a hard time to
It's hard to
find a
figure it
postdoc.
out.
It's very hard. Like most of my students graduate and they take it away. Even before they graduate, they take it away by state or federal agencies right away. I mean, it's not a it's just it's so few people actually work in that interface. The computation and the statistics, modeling and biology, ecology, and policy, and that's really I think it's a really good field. And the U.S. federal government actually created a fellowship specifically encouraging American students to study population dynamics. There is a fellowship called Pop Dye and Ecosystem Dynamics Fellowship. That's for 3 years and for PhD students. And then there's a fellowship specifically created for that to have train more American students to work on it. So here you go. Yes.
But the non-consistency, I guess, of like more sampling stations somehow having higher error, this.
Yeah.
And some of that variance that you saw, you had like a black curve and a red curve. Is that generated because there's just a certain amount of like stochasticity in the weather that year? Like somehow if you were to rewind time and do ensemble futures, would that just sort of all average out, and it has to do with the idiosyncrasies of like where you sampled relative to like microscale conditions?
That's very possible. That process errors, what we call in fishery, we have two type of errors. The measurement error,
Right.
observation, and the process errors. Process error, like what happened in the system,
Mhm.
right? Those are that's very possible.
So it might not be like in some sense, it is a failure of the statistical design, but it's really that the design is not robust to that kind of
The
stochastic.
variability, yes,
Yeah.
yeah. But the thing here is that variability will have to become worse. Think about the climate
Climate
change,
change,
right? Yeah, so it's a trend. So that I think that's actually a good idea. We probably can go back to look at it again. Because the one that we have done there is like 2008 or 9. I think we can go back. We have more years of data now. We can go back and look at it again, see whether we still see the same patterns.
Yeah.
Yeah, no, that's really good suggestion. Yes. Yeah.
It's a quick question about the V notch.
Yeah.
Is the logic that that's a way of sexing the lobsters? Because if you get one with berries, then it's female, and then you just make it less likely to catch the females, or is it?
So that approach basically you want to protect the egg bearing female.
Sure.
So for that year, but that they produce eggs and they are effective egg producers.
Yeah.
And then you want to make sure that you probably protect them for a bit longer time. So that V-notching actually extended, the season of their bearing the eggs.
Right.
And so next year, if you catch them, they don't have egg. And
But you know.
but you already, that people already see they bear egg before. And so they want to protect that kind of individuals. And we also have a minimum legal side too. So that's 82 millimeters caliper length. And those are, want to make sure that they actually have an opportunity to produce once, at least once in the life stages, like for once So that those are protected, you know,
So it's just, it's
yeah,
basically protecting the females so they can.
that absolutely, yeah, the egg production capacity.
And then the corollary question, is it, if I were to catch a lobster, would it be obvious if it was male or female or?
I think you can sex them pretty easily.
Okay.
Yeah.
So an equivalent way would be to restrict the relative numbers of females to males or something.
Yeah, so that's a lot of fisheries is a sex only fishery, like male only fishery.
Yeah.
And you see that, you know, the lot of, especially crustacean fisheries. And because, you know, you want to protect, but there's another problem because now you remove a lot of males. And you probably have, we'll call it sperm limitation issues,
Right.
and also the size one too. You got, if you have a lot of a bigger female, but only very few bigger male, then you got a problem too.
Right.
So yeah, so we kind of interesting that, you know, we also look at the sex ratios actually for American lobster fishery, but they're actually pretty close to 0.5 to 0.5, 1 to 1. Actually, so I don't know what happened. Maybe they have a compensating process to compensate actual loss of the males. I don't know, because the male only protected by the maximum legal size, not much. So they don't have that protection.
Are they, is there like a 1-to-1 sex ratio at birth?
At birth and when they have a high, you know, when the size, when a bigger one too, very close. Of course, you see more female, but it's not depart too far away from 1 to 1. So that's kind of interesting that we don't know how they compensate.
It's not like they're compensating by adjusting their own sex ratio at birth to compensate for the fact that we're only catching males.
That's possible, yeah, because we don't know the sex ratio at the birth,
Yeah.
but we only assume that 1 to 1. Yeah.
I was gonna ask, so this is for the model trying to predict the overfishing limit, like what is the, and to suggest to the government that this should be like a viable limit based on our model. Let's say the limit is like 10 units or something, fishery catches 10 units, but only like 8 of those units actually go to profit. Like they're able to get into the market in time such that they can make a profit. So there is like a 10%, 20% loss, even if they're within the limit of, within like under, they are still not overfishing, is what I mean.
Yeah.
So do companies push in the sense that you readjust your model to account for that fact that
Yeah, so
there are all these industrial limitations?
yeah, so first of all, you know, when you establish the limit, and everybody have to comply,
Right.
and so there's a you know monitoring program that keep tracking, you know, how many fish you remove it,
Right.
and make sure that you you know, within that target. If you overshoot your target, and you're gonna have to pay back next year. So we have a payback formula, like a 1 to 1. That means next year they're gonna cut down. If you're overfishing like for 5 metric tons, you're gonna pay back next year by 5. Sometimes 1 to 2. So 1 to 2 means that next year you overpay 5, yeah, you have to pay 10 back. So there are consequences. And also that, you know, if you destroy the fisheries or you overfishing the fisheries, and there's a measure kick it in, you're gonna reduce, you're gonna have a reduced TAC, total allowable catch for next year. So I think the system is designed in a way that, you know, want to make sure that everybody know there's the consequences if you violate it or if you overshooting on the target. Yeah, so I think it's a really nice system. So. Okay, any questions from online? Probably don't.
That chat was me asking, I don't see it, so.
Okay,
I think we're good. Any questions?
great. Thank you.
All right.